Hello, students. Good morning. You must be very excited that you will be going back to school soon. I'm excited too.
Hello, this is Dr. Grande. Welcome to my video comparing a t-test and an ANOVA using SPS.
Okay. Nobody is able to talk. I'm going to share my screen with you guys now. Okay. We are going to quickly go over a few stuffs here today. For a short time, we will first review what we talked about last time. And then we will go through the book, through a few readings. And then I'll just state how to find acceleration in case of friction, or a review as well. Then we'll solve a few problems. The essential thing for the last time you did was that frictional force F is less than or equal to mu R. That is the most essential thing you did last time. And we were told that frictional force is less than mu R if object is at rest and not in limiting equilibrium. Not in limiting equilibrium. And friction is equal to mu R if object is in limiting equilibrium. That is, if object is about to start moving, or if the object is moving, if it's sliding. If the object is sliding on the other one. Remember that this case is only for sliding, okay? We are talking about friction only in the case of sliding. This means you have an object, you have two surfaces, and this object is sliding. So if you have rolling, if something is rolling, the problem is completely different, but we are not going to talk about that in mathematics. I think we discussed rolling in further math, so further math students should know what we're talking about. From my demonstration last time, I made a demonstration with you guys last time. From that demonstration, what did you see? If you look in your book on page 91, there's some modeling assumptions that we have here. It says, we have assumed that the limiting value for friction is the same whether the object is moving or not. So like we have assumed this, that F is equal to mu R, whether the object is in limiting equilibrium or is moving. In reality, from what you saw in my demo last time, there is a small difference between static friction. and dynamic friction. Static friction means when the object is static, at rest. And dynamic friction is when the object is sliding. So essentially, if you have an object on a surface, if there is a force like that, and this is the limiting equilibrium force, you have F here, which is mu r, but this object is still at rest. So this is limiting equilibrium. Limiting equilibrium. And in this case, this frictional force, that F there, is static friction because the object is not moving. Now, when the object starts to slide, if you increase F a little bit more, from what you saw last time, actually you increase it to some value a little much higher than mu r. And then what will happen? The object will start to slide, right? And then you have another frictional force here. What that sentence is telling you is that in reality, for those of you guys who have studied physics, you would have seen that in physics, the assumption is not made that this friction is not equal to mu r. So let's call this kinetic friction, Fk. This one is Fs. Static friction, mu r. So what that sentence is telling you is that actually when this object starts to slide, the frictional force will decrease a little bit. So motion, in this case, motion. The frictional force, Fk, is a little bit smaller, just a little bit smaller than this Fs here. So it's a little bit smaller than mu r. If you draw the graph of friction, if you draw a graph of frictional force against this other force here, when you start to drag an object on a surface, it's going to look like this. When this force is 0, friction is also 0. When that force starts to increase, as you have seen, friction will also increase with that force. So what we are saying is that when it reaches this maximum value at limiting equilibrium, what happens is when you increase this force a little bit more, the frictional force will decrease a little bit before it then stays constant. Okay? We already saw that in our demo last time. So this value here is mu r. But because this change, so this is mu r, which is static friction. Static friction. And this is the dynamic friction here. This is dynamic friction. Dynamic friction is also called kinetic friction. If you see those words somewhere, you should understand what they mean. So what we are saying is that this kinetic friction, Fk, is a little bit smaller than Fs, which is mu r. But because this difference is so small, we just assume that both are the same in mathematics. So in mathematics, when the object is in limiting equilibrium, we take F equal mu r. Also, when the object is sliding, is moving, we also take F equal mu r. Right? That is an assumption that is made in mathematics, but you always should understand that it is an assumption. Okay? You should understand it is an assumption. We take it to be mu r, even though it is a little bit smaller. From the experiment in that, you may have realized that to start the block moving takes slightly more force than the amount required to keep it at constant velocity once it is already moving. It is just talking about what I explained. The difference is slight, and for the purpose of this course, we will ignore it and assume they are both the same. Okay, that's just explaining what I was talking about. Once the object moves, the exact point on the surface in contact with the object is always changing. So, what the second paragraph there is going to explain to you is that when this object starts to move, you'll realize that the exact points, the points that are always going to be in contact with this other object will be changing as it is moving. So the frictional force is not going to act on the same point always. But again, this is a slide. This is very slight, and we cannot account for it in mathematics, in our low-level mathematics now. So what we do is we assume that it is always going to be the same points in contact. Okay? And then thirdly, awkward shapes may make it difficult for an object to slide smoothly along a surface. Yeah, the shape of the object also matters. For example, a hook shape may lodge itself in the surface, just like if this object, if that object that is going to slide, if it has some kink like this, let's say it has some kink like this, it has a kink which we cannot even observe, we cannot see very well. Then this kink will start to, it will, maybe if this other object also has a kink, it's going to hold on it sometime, right? So effectively, you are not measuring just the frictional force will change a little bit when this object is passing through this kink, right? But again, in mathematics, we assume in this course, we are treating objects as particles, whatever the size and shape of the actual object. The size of friction will not be affected by those factors. So all these factors we have discussed, we cannot, and we are not going to account for them in our course, but you have to understand that we are making lots of assumptions here. And then I would like to, this is what we recalled last time. F is equal to mu r at the point of motion and when the object is moving. On the point of motion, or when the object is moving. Secondly, we will consider inclined plane. You will always see the word, the line of greatest slope. This phrase is going to be very common, so you have to know what it means. So if you have a slope and you have the angle is theta, let's say an object is on this slope and you are told that there is a force applied on this object, and they may tell you that the force is upwards along the line of greatest slope. Along the line of greatest slope. If you are told this phrase, line of greatest slope, just means that it is parallel to the slope. It means the force is like that, is parallel to the slope. Like that. Because we, of course, we know that you could apply the force like that. You could also apply the force like that. So the phrase line of greatest slope just means parallel to the slope. Okay? Sometimes you may hear along the line of greatest slope. Sometimes you may hear parallel to the slope upwards or something. So they may interchange. So you should know what is line of greatest slope then. In the last class, we solved problems that involved equilibrium. We would like to look at problems now in which you have to find acceleration. Remember, anything that involves forces and acceleration in mechanics, any problems that involve forces and acceleration, we have to use Newton's second law, summation F, sum of forces is equal to mass times acceleration. That's why that was the biggest thing, one of the biggest things that we studied in dynamics. So the first biggest thing we studied in mechanics was the Stewart equations. The second biggest thing is this one, F equal ma. Useful throughout our study of mechanics. So let's do an example. By the way, this example is taken from an exercise in your books. A box of mass 14 kilograms is on horizontal ground. Always remember to draw a diagram. A box is on horizontal ground. Let's draw our box. Let me make it look beautiful a little bit. You know, I like beautiful things. The mass is 14 kilograms. Okay, I see where the question is going. So there must be a force here, mg, which is 140 newtons. It is dragged by a horizontal force of 21 newtons. So there is a force horizontal And that force is 21 newtons. What did I do here? Let me make my 140 newtons much bigger, since it is much bigger than 21 newtons. Force is a vector. The size tells us about how big it is. 140 newtons. The surface is rough, and the coefficient of friction between the surfaces is 0.1. So I'll just write it here. Mu is 0.1. That is it. Resolve vertically to find the size of the normal contact force. Here you are told what to do step by step, but in most problems you will not be told. So you have R here, and you should have a frictional force here. Let's denote it F. So this problem helps you tell you what steps you should take in solving such a problem. And this box is being dragged, so there is an acceleration. If there is acceleration, you should always show the acceleration on your diagram. It should accelerate this way, acceleration A. See how I always denote my acceleration with 2 arrows, something like that. Okay. Now, we resolve vertically. Hey, this is something I have to tell you guys. When I look at your homework, most of you guys, when you are resolving your forces, you don't state what you are doing. This is also important, huh? It is clear you are telling the examiner what you are doing at this stage, okay? This means you are applying Newton's second law vertically. So either you use this or you explain in words that apply Newton's second law vertically or consider forces vertically. You have to state that, not just write down the equation, okay? It makes your work in mathematics, you have to be very clear in what you are doing. And it's like talking. It's like you are talking to somebody, so you have to be clear in your speech. So resolve vertically, we see that there is no acceleration vertically, so R must be equal to 140 newtons. Second, find the size of the frictional force. For this, you have to state that friction is equal to mu R. Excuse me. Friction is equal to mu R, and mu is 0.1, so it's 0.1 times 140. So friction is 14 newtons. Finally, find the acceleration of the box. So now, again, you have to resolve horizontally. Apply Newton's second law horizontally. Newton's second law says that the resultant force is equal to mass times acceleration. So it is 21 minus F. 21 minus F is the resultant force. That is equal to MA. That gives us A equal 21 minus F is 14 divided by M is 14. That gives us 7 divided by 14, which is 0.5 meters per second squared. So this example just gives us a simple terms what to do when we have problems to solve involving acceleration. I will go back to exercise 4B. That question I just solved was question 1. I'll look at question 3. I'll solve the odd numbered questions. And then you will solve the even numbered questions. So 3, and then 5. Hope that we will have time for that. And then 7. Okay, let's see. So question 3 says a boy is dragging a box of mass 20 kilograms up a rough slope at an angle of 12 degrees to the horizontal. The coefficient of friction is 0.28. He provides a force of 100 newtons parallel to the slope. Find the acceleration of the box. Excuse me. So we make a sketch of a diagram. Is that actually like 12 degrees? No. So this is 12 degrees. And the boy is dragging a box. Mass is 20 kilograms. So the weight of the box is 200 newtons. There's a normal contact force, R. He provides a force of 100 newtons. And we are told that mu is 0.28. Just write it down there. So we have to resolve forces. The weight perpendicular will give us 200 cos 12. And this way it will give us 200 sine 12. But there is another force we didn't include. There is going to be a frictional force, F, like that too. So the problem is solved, half solved now. So we resolve perpendicular to the slope. We get R should be equal to 200 cos 12. You can calculate the value of 200 cos 12. 200 cos 12 gives me 195.63. It's 195.63. And then we can now find our frictional force. F is equal to mu R. That is 0.28 times 195.63, which is 54.78. 54.78. Okay, remember in my problem, I left this same value in my calculator. I did not round up this value. I left it in my calculator as it was, and I just multiplied it with this to get that. Okay, it will give you a more accurate result. And then, lastly, we will have acceleration this way. So we resolve parallel to the slope. We will get 100 minus 200 sine 12 minus F should give you MA. That gives you A to be 100 minus 200 sine 12 minus 54.78 divided by the mass is 20. Okay? That second problem shows how to solve such problems on an inclined plane. We have 2 more problems to go. 5 minutes left. I will solve question 5 and maybe the next one will not be solved. A ski plane has skis to land and take off on snow. The mass of, it has mass of 3,000 kilograms and has a propeller providing a force of 20,000 newtons horizontally. It accelerates from rest on horizontal ground at 2.2 meters per second squared. Find the coefficient of friction between the ground and the ski. Okay, this is horizontal ground problem. Horizontal ground problem. So the object has mass of 3,000 kilograms. So the force here should be 30,000 newtons. There's a normal contact force R. And the propeller provides a force of 20,000 newtons. 20,000 newtons horizontally. And the acceleration is given. Acceleration is 2.2 meters per second squared. We are asked to look for the coefficient of friction, so we need to look for the frictional force, F. Resolve vertically, R is equal to 30,000 newtons. F is equal to mu R. So that is 30,000 times mu. And now we resolve horizontally. 20,000 minus F should give us the mass, which is 3,000 times A, which is 2.2. So this means 20,000 minus 30,000 times mu should be that value. That should give you mu as 20,000 minus 3,000 times 2.2 divided by 3,000 by 30,000. Is there anything new on this problem? No. We have less than 1 minute to go. And I don't think there is anything new on question number 7. All that we know is that there is a ring and there is a force. This force is applied at an angle. We have to see that the normal contact force plus the component of this force upwards should be equal to the weight. And then the force that is going to try to drive the ring along will be this force, F cos theta, where theta is this angle. And so the analysis should be the same. You resolve vertically, and then you resolve horizontally to find the frictional force. Okay? You guys should complete your homework. Thank you. For tomorrow's class, I will also not be here tomorrow. So each day, you will see your homework appear on Edmodo automatically, okay? Somebody already left the meeting. Okay, see you guys.